Good morning, everyone. My name is Meena Gowder. I'm here to talk about Firecracker for today morning's session. I'm a senior product manager at Amazon EC2. I'm also the PM for Firecracker and for burstable instances. Typically, when we talk about virtual machines, secure and fast are not two words that we use together. But Firecracker allows to create microVMs that are both secure and fast, and they're well suited for serverless computing. So today, let's dive into learning about Firecracker. So for the agenda, we will go over the introduction of Firecracker. We'll talk about the product definition, a little bit about the design principles, how it came to be. Then we'll also cover the use cases. One of the customers that uses Firecracker is an internal customer, AWS Lambda. Then we'll also look into our next customer, which is AWS Fargate, that uses Firecracker. Then we'll spend some time a little bit about Firecracker in the open source community and the engagement that it has been receiving. And then we'll wrap up. So what is Firecracker? So Firecracker is an open source virtualization technology. It's a virtual machine manager that uses the Linux kernel-based virtual machine, also known as the KVM, to create and manage lightweight virtual machines, or we call them the microVMs. So until now, you needed to choose between containers that offered fast, high performance, high density environment for your lightweight workloads, or you had to choose virtual machines that offered a very secure boundary. But with Firecracker, you no longer have to choose. The microVM provides enhanced security and workload isolation over traditional VMs, while also providing the speed and density of containers. It is also a low resource overhead. It is perfectly suited for serverless computing. It was developed at Amazon AWS. So in about November 2017, we started development of Firecracker, specifically for these internal customers, Lambda and Fargate. Lambda, when it launched in 3 years ago, it was actually meant to offer serverless compute. But over time, we saw that as more and more customers were using it, providing a single account, single instance isolation was not economically beneficial for us from a utilization standpoint. So as we were going to, just one second, let me. Yeah. As we were going through to set up look into our virtualization technology, we thought there was opportunity for us to improve how our utilization was being done for Lambda and Fargate, and that's how we started to think about Firecracker. The origin of Firecracker, it was actually started from the Chromium OS virtual machine project, which was originally written in Rust. The project was called the CrossVM. Over time, since we forked out of the CrossVM project, both CrossVM and Firecracker have diverged quite a bit to serve different customer needs, so they're very different now. So what problem are we solving with Firecracker? It's really a hard packing problem. So when we think about Lambda, Lambda offers a really good compute contract for customers that offers a lightweight environment to do their workload applications. However, it's a challenging environment for the service providers to provide a cost-efficient, at the same time provide the same privacy for customers and and also have the same kind of isolation boundaries. So if you look at this, this is kind of a typical way how a workload is consuming resources. You can think about the y-axis as any resource. It could be compute, memory, or network. And so when customers pay for their task, essentially Lambda worker has to make these resources available for the customer when the function needs to execute. So you can see that there's kind of like ups and downs here. It's not an optimal utilization of resource. So if you think about multiple end customers trying to use those resources, it really bin packs well, takes up all the utilization, but the key piece that is missing here is the isolation boundary between different tasks that are running on that workload. So we needed to use virtual machines. The virtual machines that can actually bend in this way, that are flexible. And what do we mean by bend is essentially how we can oversubscribe for resources so that when one task is idle, the other can use up the resource that is underutilized. So on top of that, if we want to bring in the isolation, similar to the virtual machines, it provides the barrier and the isolation that can support different tasks in the same secure way and still be fast and efficient. And that is essentially what Firecracker is able to offer for Lambda. So let's look at the product perspective, the key benefits of Firecracker. It actually stands on three corner pillars in how we thought about Firecracker. So security is our number one principle. Startup time or the boot time performance is our second principle. And then helping bring better utilization is our third principle. So no matter how well you put, so if you think about applications, no matter how well you put your applications and partition your accounts, when you run your applications, there are some CPU instructions that are left behind that when the host machine gets access to those instructions can potentially lead to vulnerable surface areas. But because of the minimal device model of Firecracker, it really reduces the attack surface on the virtual machines. Firecracker implements the minimal device model that encapsulates all the non-essential functionalities and reduces the attack surface area of the microVMs. This improves security, decreases the startup time, and increases our utilization efficiencies of the hardware. So let's look at the benefits from each perspective. So the Firecracker microVM, so it uses the KVM-based virtualization that provides enhanced security over traditional VMs. This ensures that workloads from different customers can run safely on the same hardware. And because of the minimal device model, it also reduces the attack surface, which provides more security. So in containers, the same kernel is shared between different guest OSs. But in the case of Firecracker, each guest gets its different or unique kernel. So there's no sharing of kernel. In addition to the minimal device space, because of the small minimal surface, it is really lightweight. So because of that, we're able to launch microVMs at a very, very fast rate. So it is designed to have a minimal overhead. You can launch microVMs in less than 120 milliseconds and at a mutation rate of 150 microVMs per second per host. So the microVM runs with reduced memory overload, less than 5 megabytes per footprint per microVM, enabling high density of microVMs to be packed on a single server. So it provides a rate limiter built into every microVM. This enables optimized sharing of the network storage resources across those thousands of microVMs that's running on the same hardware. So really the density of how many microVMs you can run on each server depends on how much resources is available on that hardware. So with Firecracker, you can see that we're making the same deep infrastructure to support serverless computing, the same way we've been investing in our EC2 compute instances. So today we support running Firecracker on Intel CPU processors, and later this year we will also be releasing support to run on AMD processors and ARM processors. We're also building integration of Firecracker to support Containerd for Kubernetes support. So let's look into our design principles. So Firecracker can safely run workloads from different customers on a same hardware. So as I said, because of its lightweight nature, it gets the lightness and the density of containers, but it also brings in the security of traditional VMs that the containers traditionally have lacked. Customers can create microVMs of any vCPU and memory configuration that is suited for their workload type. And we'll see how different customer profiles have used different CPU and memory configurations for their needs. Firecracker also allows oversubscription of resources, similar to the graph that we saw early on. That essentially is how it is able to fairly utilize all the resources that are available on the server and be able to pack as many lightweight microVMs on the server. So it has a pretty steady mutation rate. We've been able to benchmark up to 150 to 180 microVMs per host, depending on how many cores that are available on the host, 24 to 36 cores. So as I said, the number of VMs, microVMs that you can run on the hardware is only limited by the amount of resources that are available on the hardware. So later we'll see like how these different services, Lambda and Fargate, are oversubscribing these resources to utilize them optimally through Firecracker. And then Firecracker, each microVM provides guest-facing API access to the host configured, metadata for network, storage, and basic devices such as serial console, and then there's also a key for sending a Control-Alt-Del for power management as well. Yeah, and then we talked about the minimalistic guest device model, which primarily means that it supports very basic device emulation so that it reduces the attack surface on the microVMs. So here's a list of host-facing REST APIs. So you have access to the GET APIs and the PUT APIs. So the return gets the general information about the instance. So when you do a put action, you can send in a bunch of parameters. Some of these parameters are instance start. So this essentially allows you to start an instance and boot it up, get to the guest OS. Then we have the send Control-Alt-Del. As you know, it's a instruction set that is typically associated with a soft reboot in most Linux distribution. In the Firecracker side, the Firecracker associates, it exits on CPU reset. So the Control-Alt-Del can also be used for a graceful shutdown of microVMs. So it's one of the keys that is actually available, the only key. We also have the block device rescan. So the block device rescan action is used to trigger a rescan from the guest microVM after it has launched, when the host has changed the configuration of the block device so that the guest can update its data structure. So typically this action is called after the guest has been launched. We also have the GET API. So the GET API allows you to configure the machine. So when you call the GET without doing a put, it provides the default configuration of the machine, which is usually 1 vCPU and 128 megabytes. But then you can use the put to configure your VM for the vCPU or the memory configuration and all that. You can also set your drives using the devices action to set up your device ID as well. So here's the design of microVM. So the Firecracker uses the user space, the Linux kernel-based virtual machine to provide isolation. The fast startup time and the low memory overhead of each microVM enables you to pack thousands of microVMs. So this means that every function or container group can be encapsulated with a virtual machine barrier, or the jailer here, and enable different workloads from multiple accounts and multiple customers to run on that same physical hardware. You can control the Firecracker process via the RESTful API, the set of APIs that we just looked early on. It enables common actions such as configuring your instances, setting the vCPU and memory configurations for each of the microVM. It allows running all these serverless compute, which are typically short-lived workloads. So even if you need to shut down many of these microVMs and restart them, they're so fast that you don't need to maintain warm pools. So we'll look into Lambda and how Lambda uses Firecracker. So before we dive into Lambda, just a brief overview about Lambda. We built Lambda. As we build out Lambda, we're optimizing for security, reliability, for performance, and of course for cost efficiency as well. Lambda is a foundational service that is available in all AWS regions that are available today. And because it's a foundational service, any new regions that are coming up, we make sure that Lambda is available as part of the region. As we build out our systems behind the scenes, we think about how to distribute the service, how to scale up and scale down, how to work around failures and downtimes amongst different AZs so that customers don't have to worry and manage all these clusters. And of course, we do that to preserve isolation and maximize utilization as well. So just as a data point, just 3 years after Lambda was launched, Lambda is processing trillions of requests every month from hundreds and thousands of customers' active accounts today. So it's heavily used and quite popular from our customers. So one of the primary systems in the Lambda architecture is called the worker, or it's also the server, which provisions a secure environment for customer code execution. So what does the worker do? It creates and manages a collection of sandboxes. It sets limit on sandboxes such as the memory and the CPU available for the function to execute. It manages customer code and mounts it for execution. It also has multiple language runtimes that it manages. It manages or it executes code through initialization and invoke. And finally, the AWS-owned agents, it also manages the monitoring and the operation controls, like providing feeds into CloudWatch. So all that is what the worker does. So we'll take a look into the Lambda worker architecture. So at the top, you have your code, which is essentially the zip file and the layers that you want to run, or we run on behalf of the customers. Then we support a number of different languages as part of the runtime. We support Node, Java, C#, and many more. Then we have the underneath the runtime is the sandbox that hosts the runtime. This is the copy of Linux where we provide, and you're able to look into to see the file system. Then below the guest OS is the hypervisor. Typically, the virtualization is enabled through the hypervisor, and it runs on top of the host OS. Then we have the host OS, which is also powered by Amazon Linux for Lambda today. Then at the very bottom, we have the physical hardware that all the systems use. So to keep workloads safe and separate, so the code runtime and sandbox are only used by a single function from a single customer. So if a customer sends a function and then again and again, it is placed on the same sandbox from the same customer serially, so that it's not impacting the performance. However, when we run the same function on the same sandbox, they typically have a same spike or resource use pattern. So which means that all these functions are going to spike for resource at the same time, and then scale down to an idle mode at the same time. So that doesn't really resonate from a optimal resource utilization. So the guest operating systems are shared across these multiple functions in an account, but they are never shared across multiple accounts. So the boundary that we put between these different accounts is virtualization through the hypervisor that is running on top of the host OS. So with introducing Firecracker, we can do that. Before going into Firecracker, so the hypervisor essentially helps kind of slicing and dicing the physical hardware into smaller isolated environments, so that these functions can run for serverless compute, which are very lightweight. Without the hypervisor, then we don't have very small servers that can run for the scale of individual functions. So the question is, how do we manage providing the right isolation and at the same time providing the optimal security as well? So we'll kind of go into that. So let's take a look at how we do the isolation part. There are two ways we run Lambda functions today. One mode is where each worker is a separate EC2 instance. This is a great way to offer a secure boundary, and it's a fast way to build these functionalities. This is how we've created Lambda, and it's still used in the production where we use EC2 instances. But this is more of the traditional way how we did it. But then there's also the new way that we started using Firecracker. So we run bare metal instances, which are essentially the bare metal instance that you're able to access from the EC2 console. So the Firecracker microVM provides a sufficient security boundary to support multiple accounts running on the same physical hardware. So under Firecracker, we're able to run a lot of these microVMs. That gives more flexibility for us to run these functions on the same physical hardware using the bare metal instances. So this really simplifies the security model for us. So instead of having one function, one account on a single instance, we now are able to run many functions on one function per microVM, many microVMs for many accounts on the same hardware by providing the same barriers to traditional VMs that we have run on Lambda. So, and this is really good for us in a whole lot of ways, because it really helps that bin packing and improve our utilization. So another optimization that we do with Lambda is how we pick workloads and do our placements. So this is a worker or a server. When we look at this from a server perspective or a sandbox, the packing the same workload on same server, it kind of shows like each server has a similar type of workloads. So as you can see, when you pack in the same type of workloads on a single server, each of them are going to compete for resources, and it's not an optimal use of the server. However, if we are able to mix and match and use an optimal statistically loaded workload placement, then we have different type of diverse workloads that we can put up on each servers so that it mimics very similar to the graph that we saw early on, where they're each peaking for resources at different times and are optimally able to use those resources. And it also offers the same hardware virtualization-based security and isolation for each of these workloads. So we're able to have efficient, high density, while also improving our utilization. Okay. So we'll go into our next use case. We'll talk about the Fargate use case, but before we jump into Fargate, just a quick overview of the container services landscape. So we have the Amazon ECS and EKS to help manage your container services on EC2 instances. However, Fargate is a really cool service that takes all the managing part out of the customer and does the managing of the cluster and scaling of cluster and the cluster utilization. All of that is managed by Fargate, and customers don't have to worry about that. They just have to configure their functions, define the amount of CPUs and memory required to run the functions, and then load it up on ECS, and Fargate will take care of executing that at the optimal level. And the nice part is when using Fargate, you only pay for the resource that the application is using. So all the overhead is taken out of the customer's hands. Then there's also the image registry, or for container image repository, the ECR. So it's really cool to use the ECR for snapshotting container images in the repository, but it also is nice to use the ECR service for quickly scaling up and scaling down of container functions, so that you can really optimize for cost as well, based on the resource that the application needs. So here's Fargate. So Fargate is a compute engine for Amazon ECS. It does managing of all your containers and the cluster scaling up and cluster utilization. So with Fargate, you only have to think about your containers, so you can just focus on building your application and don't have to worry about managing all these EC2 instances that are running underneath. So what Fargate does in the back end is when the functions come in, it works with ECS and the underlying EC2 instances for optimal placement of those functions. So now EC2 has a wide range of instance family offerings, from general purpose, compute optimized, memory optimized, even graphics instances. The instance sizes range from the nano size, which is the smallest offering we have, going all the way up to the largest metal size. So there is quite a bit of a range, but for functions that require something as small as a quarter vCPU and 128 gigs of mem, or even half a gig of RAM, these instances are not optimal sizes. So yes, while Fargate and EC2 are doing the resource management, it is not optimal resource utilization for us. We had a problem when using EC2 instances for Fargate. So yeah, so this is kind of like the Fargate configuration offerings. Fargate offers about starting from a quarter vCPU, which is essentially time sliced, running all the way up to 4 vCPUs. And on the memory configuration side, you can start from half a gig of RAM, running all the way up to 30 gigs of RAM in increments of 1. So you're just, it's kind of like the elastic cloud coming to the next level of granularities, like the elastic resource utilization. Whatever resource that you're utilizing, you only pay for that and don't have to factor in the inefficiencies that are built into the cookie cutter instance type. So let's look into how we came from the EC2 instances to using microVMs. So in the case when Fargate was running these functions, when functions are being called, in order to place them on instances, we had to maintain a warm pool of EC2 instances that were running so that we're not launching EC2 instances. We know it takes time to launch those instances, and we don't want customers waiting for these instances to become available. So we maintain these warm pools. But with Firecracker, you don't have to maintain these warm pools, and it actually offers, so you are able to launch container-like you can launch your containers in the small, lightweight fashion, but also think about having the same kind of boundary and isolation required for the secure functioning of your workloads. You can get rid of the warm pools required because Firecracker has less than 125 milliseconds of boot time. So as soon as a function is being called, a microVM can be spun up based on the resource configuration that the task is looking for. And Fargate already takes care of placement of all these functions optimally on different servers so that you can benefit from oversubscription as well, making sure each microVM has the resource it needs, and it takes care of the placement on the resource that is able to offer the required resource configuration. Yeah. And then we also have multi-AZ availability so that you have high durability for accessing these functions. So I talked a lot about improving our utilization while maintaining security and providing the same isolation boundaries. What does this all matter for customers? If we're able to improve our utilization and bring down our cost, it essentially translates back to passing on those cost efficiencies back to our customers through price reductions. And so earlier this year, I believe this was in January, after we launched Firecracker and both Lambda and Fargate started adopting Firecracker, the efficiencies that Fargate was able to achieve from Firecracker essentially translated to price cuts for customers who are using Fargate. So if you can see some of the popular services, the 2 vCP and 16 gigs of RAM, we were able to achieve up to 50% price reduction earlier this year. Let's look into briefly the Containerd integration with Firecracker that AWS is working on. So as you know, Firecracker is an open source project, and within Amazon there are many open source initiatives that are underway. One such project is the Containerd integration that we've been working on. So our objective to integrate with Containerd is to manage containers as Firecracker microVMs. So the project, the Firecracker-Containerd essentially allows supporting multi-tenant hosts for containers. So it uses as much as possible, we're trying to adhere to the OCI image format that is very typically used in the container ecosystem, so that it could be closer to a plug-and-play experience for the container ecosystem users. We're working with popular orchestration frameworks to make it work with Kubernetes is one of our goals, and with Containerd integration, we'll be able to support with our ECS as well. And why we want to do this? It is helping define the future. As much as we have all benefited from having a lightweight and the efficiencies with containers, we also want to bring in the security that we've come to benefit from traditional VMs. So with Firecracker integration in the container ecosystem, you get the benefit of both. So here's a quick architecture of the Firecracker and Containerd integration, or the stack. So it essentially has three components. It has the snapshotter, it has the runtime, and then it has the agent. So the agent is linking the Containerd outside from. The runtime is linking the Containerd outside of the microVM. Then we have the snapshotter, which is an in-process component. And then we have the microVM, which has a built-in agent that is able to invoke the runC and execute the containers within the microVM. Then we'll kind of briefly talk into the community engagement. So Firecracker as an open source project. So last year, we announced the Firecracker open source project at re:Invent. So internally, we decided to open source it around late October. So between late October and November, when we announced, we had very little runway to actually get the code all ready for open source, get the documentation put together. We were super excited about open sourcing the project, the initiative. So since we open sourced it, the responses have been overwhelmingly encouraging. So we've got a lot of feedback from the community members, both from how to run Firecracker, not only on AWS, but also in other cloud environments. We've got a ton of inputs on how to improve our documentation, our governance process. We've also had a lot of bug fixes and reports, several feature requests that have come in, all of which are tracked in our GitHub repo. So as you can see, like about 27% of our pull requests are from community members. Based on customers' interests, we've presented 12 different industry conferences, not only by AWS employees, but we've also had presentations provided by the open source community members as well. So a nice thing that has evolved from the Firecracker open source initiative is the Rust VMM project. So the Rust VMM is an initiative that kind of organically grew based on building virtual machine VMM blocks for different functionalities. And this was an initiative that came together through the collaboration from multiple participants from Google, from AliCloud, from CloudForge, Intel, who are all working towards the same ideology to build modular VMM functionalities, and then they all came together to build the Rust VMM project. It has had very good engagement from all these customers or community members, and we have currently 3 crates already available in the Rust VMM GitHub repo, and more are in the works to put in there. So interestingly, when we started working on the Rust VMM initiative, Red Hat also announced that they're thinking about the QEMU VMM to use a modular fashion as well. So in using Rust language. So it's kind of interesting to see how the Rust VM project has kind of started to take shape, and the industry is also kind of looking in the same space. So we'll also look into the integration of Firecracker with other orchestration providers. So one of the key partners that we've been working with is the Kata containers, and we'll talk about Kata containers in the next slide at a bit more depth. We've also had integration with UniK. So UniK is an orchestration platform for lightweight VMs. It provides tools for compilation and management of applications, turns it into unikernels that can run as bootable disk images in microVMs or the traditional lightweight VMs as well. So UniK runs and manages unikernels and microVMs on a variety of cloud providers and also on local machine. So earlier in January, UniK integrated with Firecracker. Then we have OSV. So OSV is a virtual modular virtual machine that enables to run unmodified Linux applications in the cloud as well. So they came up with a Python script to launch Firecracker microVMs that is available. There's a blog on OSV how to use it as well. So they've been able to launch Firecracker microVMs under 10 milliseconds. So it's like 5 milliseconds for their own device modules, and then another 5 milliseconds to actually launch Firecracker. So it's pretty interesting there. So let's talk about the Firecracker and Kata integration. So the objective of Kata containers was to build lightweight virtual machines that seamlessly plugs into containers, but it was going down the path of using traditional QEMU-based hypervisors. That is a integration that it had available last year. However, it was intentionally set, or one of the design principles for Kata containers is to be hypervisor agnostic, or to be able to embrace any or many hypervisors that it can support. So integrating with Firecracker was something that was very interesting for Kata containers right from the beginning. So when we announced the open sourcing Firecracker last year, they've partnered with us and been working about integrating Firecracker with Kata containers. So here's a view of what the Kata container integration looks like. So it can utilize both runc on this side, Kata with Firecracker, or Kata with QEMU, all within the same Kubernetes for each workload, for in each containers. So to achieve this configuration, the cluster must be configured to use either the CRIO or containerd, and it must use the runtime class name tag. So you can see this is a sample YAML snippet on how to define the runtime class name tag on what type of hypervisor your container wants to run. And the interesting part is within the container, each workload can use different types of the hypervisor as well. So if you want to change from Kata FC to using Kata QEMU, you just change the runtime class name from Kata-FC to Kata-QEMU. So we ran into some technical difficulties, so as backup, I had a little video done together. So here's like the video of how we launched like a group of microVMs that was launched to do benchmarking for networking. You can see each of these little blocks are microVMs that get launched in groups, and this is done we did this to measure the boot time of like a group of microVMs running on a i3 metal instance. In the beginning, you can see that little trail of blocks is essentially the amount of network resource it is using while launching, but after some time, those tails will go away. So at a given time in each groups, we launched about 150 microVMs on each of them to see what is the launch time for each of them. So here's a graph that shows the metric. All of these little sprinkle dots are microVMs and the average time, or the time it took to boot up. So you can see that the mean average is about 152 milliseconds that we were able to measure on an i3 instance. We should be able to get better performance with M5 metal instances as well. And then the shortest time to launch microVM was 123 milliseconds. The highest it took was like 219 milliseconds. So it's pretty fast. And the fact that you're able to launch about 4,000 microVMs on a single hardware really speaks for how well you can utilize the resources. So who should use Firecracker directly? So teams trying to build compute services. So obviously within AWS, we have service teams like Lambda and Fargate who are using Firecracker. We're also working with other internal services that need the same lightweight environment like containers with the isolation barriers like a traditional VM. So if there's an opportunity for them to use something like Firecracker, both the teams kind of work together. So we treat our internal services also like customers. We also are working with the traditional container stack providers to see opportunities to integrate Firecracker with them. So they're also using Firecracker, like Kata containers. And then we also have developers who want to contribute to the Firecracker initiative or any of the initiatives that are tied with Firecracker, like the Rust VMM should also be using Firecracker. How to get started? So there's a bunch of information about how to set up and launch a Firecracker and see some of these demos for yourselves. You can run Firecracker on AWS bare metal instances. You can just grab these metal instances from the EC2 console or through the API. We also have tested and have instructions on how to run Firecracker on other cloud providers on bare metal instances. We can also run Firecracker on GCP's nested wort, so there are instructions for that as well, and on Azure. And then you can also run Firecracker locally on your machines as well. Then there's this nice little Firecracker CLI, which is just a binary that you can download to use to create Firecracker VMs. This is available in the GitHub repo as well, so you can check it out. Yeah, and then this is our GitHub repo. Anything that you want to learn about Firecracker, all the information that I shared today, all that is documented in our Firecracker GitHub repo. It is it is a live open source project. So all our development for Firecracker is happening in the open. All the issues on features that we are developing are tracked as issues. We regularly groom those issues, and we have a roadmap that is published on a frequent basis. So if you have any interests, comments, features that you want to see with Firecracker, feel free to reach out there, create an issue, and we'll groom that in our next sprint. We also have a Slack room where all of our developer engineers are in the Slack room, and it's very chatty, very responsive. A bunch of our Firecracker development team is based out of Bucharest, Romania. And then we have few members here in Seattle as well. So between Europe time and US time, you pretty much have a 24-hour response that people always respond back on Slack, so I always have my phone going on buzz. So that concludes our presentation. Hopefully you had the opportunity to learn something about Firecracker and how we're able to achieve the security and speed and performance of VMs and containers in a single environment. If you have any questions, I'll hang out here after the presentation. I think we have a next presentation at 9 o'clock, so I will wrap up. Thank you for coming today morning. Yes, and don't forget the survey. Thank you.